All right, this is a big ideas tutorial for the Algebra 2 book, section 1.1, parent functions and transformations. So we're going to talk about different families of functions. Those are just groups describing transformations of those parent functions and describing combinations of transformations. So first thing is that functions that belong to the same family are ones that share the same key characteristics. A parent function is the most basic version of that function of the family. So a couple of the examples down below of parent functions, a constant function, which is just a horizontal line, y equals 1, a linear function, y equals x, where it crosses through the intercept and has a slope of 1, y equals the absolute value of x, or y equals x squared for a quadratic equation. Notice how instead of y, some of them you're seeing f of x. That means the same thing as y, that just means the function of x. F stands for function. So functions in the same family are transformations of those parent functions. So of these 4 examples of parent functions, there are a couple different ways that you can move them around, switch them, flip them, stretch them, to make them look a little bit different, but still have the same key characteristics of these parent functions. So first, there's a f of x equals 2 times the absolute value of x plus 1, and we need to identify which function family that this belongs to and compare this graph to the graph of its parent function. So the graph of this f is a V shape with a straight lines and hard points and no curves. So f of x is going to be an absolute value function. Compared to its parent function, the graph is shifted up, and it looks like it was a little bit more narrow than the graph of the parent of the absolute value function. The domain, which is all numbers left and right, is all real numbers when this graph continues on. But the range is of all the y values that are greater than or equal to 1. It does not go below the y value of 1, but the range of the parent function is y is greater than or equal to 0. So it looks like it's been moved up from 0 to 1, and then it's been stretched vertically so that it looks a little bit skinnier or more narrow than its parent function. So you can also use a couple different rules to identify the functions. The only variable term in the f is the absolute value of x. So just by looking at those vertical bars compared to the parent function we talked about earlier, that absolute value is still there, and those bars are still there as well. Okay, so now if we look at just starting the graph when given the function and graphing its parent function while describing a transformation. So g of x, again, means the same thing as y equals x minus 4. So the parent function of x is crossing through the origin and going up 1 over 1 for the slope, so that is its parent function. The new function takes the form of y equals mx plus b, where m is your slope, but b is your intercept. Our m is still 1, so the slope is not changed, but the y-intercept is now -4. So we're going to draw a line through the point 0, -4, and have a slope of +1, so going up 1 over 1. So the new graph of g of x looks like it's shifted down 4 units below the graph of its parent function. So it's a vertical translation is the actual terminology of this shift, 4 units down of the graph. Looking at a new one, graph p of x is equal to -x squared in its parent function, then describe the transformation. So the function p is quadratic because it has an exponent of 2. It looked like this parent function that we talked about on this slide right here, x squared. So we're going to use a table of values to help graph the parent function and its new function. So -x squared is written in function notation. Again, p of x is just another name for y. So we're going to use a couple different x terms, 0, +1, +2. And when you plug those in to just the regular x squared function, 0 squared is 0, 1 squared is 1, 2 squared is 4. Same thing going on to the negative side. So if you use -1 squared, you get +1, -2 squared, you get +4. I don't know why these values are not showing, but they should be -2 and +1 right here. And then plotting those 5 points gives you the graph that is your regular quadratic parabola shape. Now, if we plug it in with the negative x squared simply reflects that graph over the horizontal axis so that it points down. You're pretty much taking any value in your middle column and putting a negative in front of it. So instead of this 1 right here, it's now a -1. Instead of this 4 right here, it's now a -4. That is the only thing that you're changing, and 0 stays the same, and those two graphs intersect. So the graph of P is the graph of the parent function flipped or reflected over the x-axis. Okay, looking more at continuations with stretching and shrinking, g of x is 2 times the absolute value of x. So we're going to look at first our table of the graphs, and we're going to pick the points 0, 1, 2, -1, -2. Plugging those in to the parent function, which is just the absolute value of x, is the exact same thing. So it's +2, +1, 0, +1, +2. That is the parent function of the absolute value of x. Then plugging it in where you're taking the absolute value and then multiplying by 2, you're essentially taking all of these values and multiplying them by 2. So instead of 0, it stays 0. Instead of 1, 2, 2 to 4, you're just multiplying everything by 4, which means you're kind of stretching these vertically. When you think of the word stretch, I want you to think you're taking the top and the bottom and pulling them further away from each other. Is that stretch? So the y-coordinate is 2 times the y-coordinate of the parent function. And again, talking about vertical stretches again from the parent absolute value function. Moving on to part D, which is the quadratic function. We're using 0, 1, 2. Formatting on this is not importing well, so I apologize. But using that same quadratic function of x squared, you get those 5 values. So your quadratic should look the same like the previous example that we've done. But now what we're going to do is, and that's not importing, so I'm going to go back, is take 1/2 of each of those values in the middle column. So we're going to take what we got and divide them by 2 or multiply times 1/2. So half of 4 is 2. Half of 1 is 0.5. That should be right here, 0.5. Same thing down here on this side, 0.5, and then half of 4 is 2. So it is being shrunk vertically or compressed vertically. I don't want you to think of stretching horizontally. I want to think of all of our stretching compresses happening vertically. So we're compressing it down vertically so that all of these y values are being smushed down closer to the middle. So 1/2 of each of the corresponding points from the parent function, and it is a vertical shrink. You might hear me say the word compress a lot as well. So to visualize that pulling and shrinking, you're taking opposite ends at the top and the bottom, pulling them apart, or you're pushing them together. Do not think about this as a left and right stretch and compress. It is an up and down, pulling them apart or compressing them down vertically. All right, using the graphing calculator to graph g of x is equal to negative absolute value x plus 5 minus 3 and its parent function, describe the transformation. So there are multiple different transformations happening here. The parent function of this is an absolute value because you see the bars. So that black one right there is what the parent function f is, and then your g function is what the new one looks like. And you can go into a graphing calculator on the internet and just type in this function, and this is what it's going to look like in this red g graph. So it is 1, a reflection. It is being flipped down to the bottom below the x-axis. And then it is being moved to the left 5 units, and then it is going down 3 units to get your new function. That is the description of that transformation in that order. So reflection is first, and then you are translating it. You can't translate and then reflect. So let's look at one last real-world problem. So this table of data points shows both the height of a dirt bike after X seconds of jumping off of a ramp, what type of function can you use to model the data, and we're going to estimate the height after 1.7 seconds. So let's think about what the problem is asking. we need to, one, identify a type of function that can model the table of values, and then find that height after a specific time when we plug in for our x. So let's create a scatter plot of the data and then use the relationships talked about from the parent functions after we create that function to estimate what it would look like at 1.75. So when you plug in these points into a scatter plot of x and y, it should look something like this, of just the points. And when we connect those dots, it looks like it is similar to a quadratic function when we draw the line through. So that's what our parent function is going to be based off of, is this quadratic graph. Sketch that curve. And then by looking at the graph, we can kind of estimate based on where 1.75 seconds is right here, that it looks like it's going to be about 15 feet. Again, in the directions, it says the word estimate, so we are not actually finding a model or an equation. We are just looking at the graph and estimating what it is going to be close to. So let's check the solution to see if it's reasonable and analyze our values in the table. So we're looking at something between 1.5 and 2 on our seconds. It looks like it's increasing from 8 up to 24, and then after 24, it goes back down. So our value should be somewhere between 8 and 20, and guess what? It is. 15 is between 20 and 8. So that would make sense that it is descending at 1.75 seconds.